So let's look at writing the electronic configuration for the elements. We start first with the main group elements, and then we're gonna move on to transition metals and see how we can write the electronic configuration for the transition metals. And then we show you some trends in the periodic table where you can tell the electronic configuration by just looking at the location of your element in the periodic table. And we also show you what information you can get from the periodic table. So based on the orbitals that we have, we want to put the electrons inside these orbitals. A couple of things that are important here is that, first of all, the energy of the orbitals and sublevels is extremely important. So you want to start from energy level 1 and S sublevel. If you have electrons available, then you move on to the second energy level and then you fill out S and P. Now in the second energy level, it's important to fill up S sublevel before you move on to the P sublevel. It's all about the energy. So the orbitals that have the lower energy are going to fill up first, and the orbitals that have a higher energy are going to fill up next. And also remember that the maximum number of electrons you can fit in each orbital are 2 electrons, and the 2 electrons have to have the opposite spin based on the Pauli exclusion rule. Now we're going to show you different examples, and as we do examples, we learn different principles and we learn any exceptions that we have. Now there are different ways that we can show the electronic structure. Before we just wrote the number of electrons, protons, and neutrons, but now we want to focus on electron configuration. So we're going to use SP to write the electron configuration. And the reason we're focusing on this for now is because we're more interested in the number of electrons and the energy of the electrons in general chemistry. We want to show you bonding, and bonding is done through the transfer of electrons. So we want to identify those electrons that participate in any sort of reaction or bonding. So we're going to use electronic configurations. And again, just to remind you, the order in which the electrons are filled up. So we start with 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So after 4s2, that's when we have the exceptions. For now, let's just practice on the first 18 elements. And once we master this, then we move on to transition metals. So I also showed you the box diagram. So we can either write the number of electrons, protons, or neutrons, or we can write the electronic configuration, or we can also do the box diagram. So for these first 18 elements, we're going to practice writing the electron configuration and box diagram. And as we learn more principles and rules, then I show you how we write electron configuration for ions and also for transition metals. So let's start, for example, with helium. That's on this slide. So we're writing electronic configuration. So the number of electrons are important. So helium, how many electrons would you expect for helium? 2. Now, since it has 2 electrons, electron configuration is 1s2. And the orbital diagram, this is the 1s orbital, and you have 2 electrons in it. So we want to write the electron configuration and box diagram for different elements. So let's practice a little bit. So for hydrogen atom, we want to write the electron configuration and also the box diagram. So you look in the periodic table, and based on the periodic table, you expect 1 electron for the hydrogen atom. So the electron configuration for hydrogen atom is 1s1. because I only have one electron. Now for the box diagram, since it's a S, we only expect one box, and I label it as 1s. And how many electrons do I expect in here? 1 electrons. Now let's move on to helium. Helium has 2 electrons. So the electron configuration of helium is 1s2. And the box diagram, you expect one box. You label the box, it's a 1s, and you expect 2 electrons in the 1s box. Now let's look at lithium. You want to write the electron configuration for lithium. Lithium has 3 electrons. So the electron configuration is 1s2, 2s1. For the box diagram, we have the 1s and 2s. In the 1s orbital, we have 2 electrons. In the 2s, we have only 1 electron. Now moving on to beryllium. Beryllium has 4 electrons. Electron configuration is 1s2, 2s2. Now in terms of box diagram, since we only have s orbitals, we expect 1 box for each. In the 1s, you have 2 electrons. In the 2s, you have 2 electrons as well. Now let's move on to elements where the p sublevel is being filled up. So for boron, boron has 5 electrons. So the electron configuration for boron is 1s2, 2s2, 2p1. Now in terms of box diagram, we have the 1s, 2s, and 2p. In the 1s sublevel, we expect 2 electrons. 2s, 2 electrons, 2, 2p, only 1 electron. So you want to write the electron configuration for boron. And boron has 5 electrons. So boron, 5 electrons, 1s2, 2s2, 2p1. For the box diagram, we have the 1s that has 2 electrons, 2s also 2 electrons, and then the 2p only 1 electron. So for carbon, carbon has 6 electrons, so the electron configuration is 1s2, 2s2, 2p2. So box diagram, 2 for 1s, 2 for 2s. And then for the 2p, yes, we have 2 options. We could either put the 2 like this, or we could put both of them in one orbital. So now in this situation, we're gonna look at Hund's rule. So Hund's rule says that you put one electron with the same spin in each orbital, and then you come back and pair it up. So we can't put two electrons in one orbital initially. You put one electron in each orbital, then if you have extra ones, you come back and you pair it up. So for nitrogen, which has 7 electrons, electron configuration is 1s2, 2s2, 2p3. And the box diagram, we have 2 for 1s, 2 for 2s, and 3 for 2p. So 1, 2, 3. And then for oxygen, where the number of electrons are 8, so 1s2, 2s2, 2p4. This is how the box diagram looks like. So 2 in the 1s, 2 in the 2s, and for the 2p, we go 1, 2, 3, and then 4. So let's look at fluorine here. Number of electrons for fluorine are 9. So electron configuration is 1s2, 2s2, 2p5. The box diagram, we have 2 for the 1s, 2 for the 2s, and 5 for the 2p. 1, 2, 3, 4, and 5. And also let's look at neon. Neon has 10 electrons. So 1s2, 2s2, 2p6. So 1s, 2s2 electrons, and the 2p of neon is going to be completely full. So this table also summarizes the electron configuration and box diagram for the first 10 elements. So let's look at the electron configuration and box diagram of sodium. So the number of electrons for sodium is 11. So the electron configuration is 1s2, 2s2, 2p6, 3s1. And this is the box diagram for sodium. So on the slide here, you see the electron configuration for the first 18 elements. Please practice writing the electron configuration and also the box diagram. Now let's look at the valence electrons and valence shell. So as I mentioned earlier, what's important to us is the electrons, number of electrons that are available, accessible for formation of a bond or doing chemical reaction. Also the energy of these electrons are important. So we want to focus on valence electrons here because valence electrons are going to be the electrons that are accessible, available to do chemical reaction, to be transfer or share and do any sort of formation of a bond. So valence electrons are the outermost electrons. So those are the electrons located in the highest energy level orbital of the atom. So we basically want to show you that only valence electrons participate in the transfer or sharing of the electron, and the core electrons don't really do anything because they're not accessible, they're not available. So how do we identify valence electrons? So you look at the electron configuration. So for example, here this is the electron configuration of oxygen, 1s2, 2s2, 2p4. So valence electrons are the electrons in the outermost orbital. So the highest energy level are 2s and 2p. So these are the outermost orbitals, or we call them valence shell. So your valence shells are 2s and 2p, and number of valence electrons are 6 valence electrons, because you have 2 in the 2s and 4 in the 2p. So in order to identify the number of valence electrons, you write the electron configuration, and based on the electron configuration you find the valence shell, and once you identify what the valence shells are, you look at the electrons on those valence shells. So we ask you for the number of valence electrons. So let's look at another example. You want to know how many valence electrons phosphorus has. So phosphorus has 15 electrons. So electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So in order to find the valence electrons, we need to identify the valence shell. 3s and 3p are valence shells. So those are the outermost sublevels. And you have 5 electrons total in 3s and 3p. Let's do another example. Which element could have the following electron configuration? So in order to see what element, and it says element meaning that it's neutral, so we gotta count the number of electrons here. So we have 2, so 2, 2, 6, 2, and 6. A total of 18 electrons. And if you look at the periodic table, argon has 18 electrons. Now let's look at the periodic table and see how the electronic structure of the atom relate to the position of the elements in the periodic table. So elements are not randomly positioned in the periodic table. So we can actually look at the electron configuration of the elements by just looking at their location in the periodic table. So remember, there are 2 ways that we read the periodic table. Groups are columns when you go up, down, and we have 18 groups. And periods when you cross the periodic table, or we call those rows. Now in the periodic table, keep in mind that the period number corresponds to the highest principal quantum number of n of that element, and group number represents the number of electrons in each orbital. So what does that mean? So for example, if you look at hydrogen, hydrogen is in period 1, and it's the first element of period 1. So these period numbers basically represents the n. So any elements in period 1, n equals to 1 is being filled up. Any element in period 2, n equals 2 is being filled up, and so on and so forth. Now, in energy level 1, we only have sublevel S, right? And in S sublevel, we can have a maximum of 2 electrons. Now look, 1, 2. So these are called S block elements, meaning that the S sublevel is being filled up. Now, P sublevel was a maximum of 6 electrons. Now, if you move from group 3A, 1, 2, 3, 4, 5, 6, and these are called P block elements because those represents the electrons in the P orbital. Now, what does that mean? For example, look at hydrogen. I'm just looking at the periodic table to come up with the electron configuration of hydrogen. Hydrogen is in period 1. So this is for the hydrogen. Now, hydrogen is an S block element. And hydrogen is the first element of the S block. So the electron configuration of hydrogen is 1s1. Now, if I move to lithium, so I'm trying to write or come up with the electron configuration of lithium by just looking at the periodic table. So lithium is in period 2, meaning that period 1 should be completely full, anything in period 1. So 1s2 is full. In order to get to lithium, you have to pass through period 1, hydrogen and helium. Now lithium is in period 2. Lithium is an S block element, and lithium is the first element of the S block elements. So that's the electronic configuration of lithium. Now let's look at, for example, nitrogen. So nitrogen is in period 2. So everything in period 1 should be completely full. Now nitrogen is in period 2. And nitrogen is a P block element. So 2s needs to be full until we get to the 2p, because nitrogen is a P block element. Now nitrogen is the third element of the P block. So 1s2, 2s2, 2p3. Now let's look at magnesium, for example. Magnesium is in period 3, meaning that first energy level and second energy level should be completely full. Magnesium is in a third energy level. Magnesium is an S block element, and magnesium is the second element of the S block elements. So that's the electronic configuration of magnesium. So let's say I want to do argon. Argon is in a third energy level, meaning that all the orbitals in the first and second energy levels are full. Now argon is a P block element, so meaning that S is completely full and we are in the P. And argon is the last element of the P block elements. So that's the electronic configuration of argon. Now, for main group elements, based on their location in the periodic table, we can find out what the valence shells are, and we can find out the number of valence electrons for them too. For example, let's look at nitrogen. Here is the electron configuration of nitrogen. Valence shells for nitrogen are 2s and 2p, right? And look, nitrogen, it is in period 2. So the period number gives you the valence shell of each element. Now, number of valence electrons for nitrogen is 5, and nitrogen is in group 5. So group number, and it is only for main group elements, group number equals to number of valence electrons. So this is very important to know because oftentimes we need just the number of valence electrons for when we do, bonding. We just need the number of valence electrons. So you can look quickly at the periodic table and look at the group number and find out how many valence electrons you expect. And keep in mind that group number equals to the number of valence electrons only for main group elements, not transition metals. So another one, for example, if you look at magnesium, look at the electron configuration, it ends with 3s2. So your valence shell is the 3s and magnesium is in period 3. Based on electron configuration, the number of valence electrons are 2, and look at magnesium. Magnesium is in group 2. So same thing with argon. Valence shells are 3s and 3p. Hence the reason argon is in period 3. Number of valence electrons based on the electron configuration are 8, and argon is in group 8 too.